We have already discussed electromagnetic waves. We have already introduced the idea of a wave, right? Now, last class, we finished with our lecture on electricity. We talk about charges, static electricity. We talk about the forces between charges, electric field, right? Circuits, Ohm's law, applications of Ohm's law. But we didn't go really in depth to many applications of electricity and magnetism, right? Now, you should know that the person that combined or unified electricity and magnetism was James Maxwell. And he took the results that we got from different parts of electricity and magnetism. One of them will be Gauss's law, Faraday's law. He combined them into what we know the four Maxwell equations. Now, that's not really the aim of these two chapters, but at least it's a good way to start, right? So you guys can know or can remember, right, where many of these things come from, right? Because now in this chapter, or in this chapter in particular, we will be discussing electromagnetism, and the first part of the name, right, electro, comes from electricity. And then we have magnetism, which is basically the study of magnetic fields. So normally in schools, the best way to introduce magnetic fields will be with a nice experiment where you can use two magnets or just one magnet, normally a bar magnet. And we emphasize the difference between magnetism and electrostatics, where in electrostatics we had electric charge, positive and negative, but in magnetism, or in the case of a magnet, we have the north and south pole, as you see there. We have many shapes for magnets, right? You can have bar magnets, U-shape, circular magnets as well. And the idea is to investigate what happens when you approach different materials to a magnet and to study the magnetic field itself. But it's also important to notice, right, that in the case of a magnetic field, or in the case of a magnet, we always have them coming in pairs, north and south, the poles of the magnet. That's not the case with electric charges, right? We have the proton, which is positive, and the electron, which is negative, and we know they attract, or two protons repel, but they are point charges. You can have an overall positive charge, and the basic of it, which is the charge of the electron, right? Remember that the proton and the electron, they both have the same charge, it's just that one is positive and the other one is negative. Now, with magnets, something that I want to make sure that it's clear, it's not possible to have what we call in physics a magnetic monopole. So, if you cut a magnet in half, you won't get north and south divided or separated. You will have each piece with its own north and south pole. And that's actually very interesting, because that means that wherever we go, when we investigate magnets and magnetism, it will always come in pairs. Now, it's true that the new theories in physics, for example, string theory, they allow for exotic states of matter, right? Remember that when we discussed in chapter 4 the states of matter, I mentioned that there are other states of matter that we call them exotic. For example, neutron stars, white dwarfs, black holes. They are some sort of matter that sort of do not fall in any of the solid, liquid, gas, and plasma state, right? They are more like electron-degenerated matter and so on, due to the enormous amount of pressure. Now, we also think, theoretically speaking at least, that magnetic monopoles may be allowed in certain circumstances. There was an expedition to the North Pole a few years ago where they were trying to look for these magnetic monopoles, right? We may not find them here on Earth, but we might find indications or evidences of them out there in space, right? So what do we know of the magnetic field of a magnet? You know what's the best way to introduce or to understand this? And let me show you that in the whiteboard. Is when we talk about the Earth. If there is something that I want you guys to know, right, is that there. Oh. Wait. The whiteboard, wait, let's see. Maximize. Okay, there it is. So there's something I want you guys to know, is that the Earth is a magnet. How come? When you have the illustration of the Earth, never forget that at the core, in the core, we have an iron nickel core, and we have the molten core. So the outer core and the inner core. It's not to scale, by the way, because in fact, let's actually make it like that. There you are. So this is the molten one. And the inner core will be this. The outer core that is molten is spinning quite fast. You have iron and spinning conductive material. That's the basics for the production or creation, in this case, of a magnetic field. You guys remember that a current has some sort of direction in a circuit. We are going to be analyzing this in this chapter. But what I want you to understand is that since you have the core, iron, and molten, spinning quite fast at 1,000 kilometers per second in some cases, right? Or, yeah, approximately, right? This material will have a magnetic field that actually goes like this. So the north magnetic pole is here, and the south magnetic pole is here. And look how, just like the axis of the Earth, is a little bit tilted. All right, it's not really vertical. It's important to notice that, right? Yes, I think I can figure it out. Okay, let's put these lights away. I don't wanna. So these are the magnetic field lines. Now, there is a difference with the electric field lines, right? When we have a point charge, just a point charge, I'm not talking about a positive and a negative charge, just a point charge, we have the electric field going like this, away from the charge. Right? Now, this diagram may look similar when we put here a negative charge and then we look at the interaction, sort of like the interaction between the north and the south. Remember that the Earth is tilted 23.5 degrees. The axis of the magnetic field is approximately 6-7 degrees difference between the tilt of the Earth and the axis, the magnetic axis. Now, that tilt is important because due to the tilt of the Earth, we have the seasons, right? Because as the Earth goes around the Sun, one side of the Earth, in this case right now the South Pole, will be facing closer to the Sun. Not closer, but towards the Sun. During June, it will be actually the North Pole, and then that's why the South gets winter. Now, this magnetic field is normally found in the magnetosphere, which is a very small layer in the atmosphere between the mesosphere and the exosphere. Now, the magnetosphere, right, which is basically where we find the magnetic field, is another important factor for life because, as you should know, the sun is the key for our life, but also it can be very harmful, right? There is solar wind, solar radiation, and just like the ozone layer protects us from the UV rays, and we're going to learn about UV rays when we go into electromagnetic waves. UV rays is just one part of the spectrum of light, all right? So when this solar wind goes or is expelled from the sun due to a solar flare or any activity in the sun, right? The Earth's magnetic field is acting like a shield. So when the solar wind, I'm going to use this by the way, hits the magnetic field protecting the air, right? What happens is sort of like a slingshot effect. The magnetic field gets elongated to the point where the radiation, due to the interaction with the particles in the ionosphere, go towards the poles. And we actually have evidence for that. You know why? Because that's the physics behind auroras and the northern lights. We can observe both of them due to the interaction of the solar wind or solar energy or solar wind with the atmosphere. Normally that's what we say, right? And when it's actually the magnetic field, the one that is interacting with the solar wind. Now, what you should also know is that those colors that you see are also due to the excitation of ions, of atoms in the atmosphere. So, we see colors due to the emission and absorption of photons, which again, it's more part of electromagnetic waves, but is a direct application of magnetic fields. In this case, the magnetic field here on Earth. Now, the magnetic field here on Earth is important, but it's not very strong. It's approximately 1 Gauss, which is approximately 20 microteslas. Gauss and Teslas are the units that we use to label or to measure magnetic fields. We know that electric fields, the units are newtons per coulomb, right? The electric force per unit charge. A magnetic field, we label it with the letter B. We don't use M because M is used for another variable that we use to classify magnetic materials, the magnetism. There are actually 3 types of materials: paramagnetic, diamagnetic, and ferromagnetic. Ferromagnetics are the ones that you normally see that are attracted by a magnet. But you have diamagnetic and paramagnetic. One of them, the paramagnetic, actually is very important because we use those materials to study the history of the magnetic field poles. You should know that, as I show you on the whiteboard, the magnetic field right? The poles of the magnetic field are north on the geographic south, south on the geographic north. But we know by studying paramagnetic materials, we call that in earth science paleomagnetism, we know that the poles of the magnetic field of the earth have switched throughout history. We do that by studying paramagnetic materials, the bottom of the sea. Okay? So, that's actually a good introduction now, to show you the magnetic field is important, how it can be created by a moving current or a changing current, but also by a moving charge or an accelerated moving charge. And the interesting thing is that we actually study first the interaction of current and charge with the magnetic fields. For example, in the case of a force, right? Let me show you what I'm talking about right now. Oh, wait. Am I trying right now? Okay. I hope that you guys were watching the whiteboard. I don't know if anyway, here. If we have these magnets, right, as I told you, you break this in half, you have a north and south, north and south. Now, just as you will expect, opposite poles attract, like poles repel. So what we have here is that the south will be attracted to the north. Okay, like that. And if you have the north pole and the north pole, it will be repelled. Interesting enough, when you guys have a magnet like that, a ferromagnetic material like iron gets attracted to the magnet. That's because automatically it's sort of like poles in the iron are induced. And that's going to be very important when we talk about the relationship between electricity and magnetism, by the way. Okay? Now, when can we use magnetic materials for the deflection, for example, of a compass? You can have a compass pointing towards the north due to the magnetic field existing around a certain region, right? Now, something that you guys should also know is how does the magnetic poles or the magnetic field looks around a magnet. If you remember what we did in electricity with a positive and a negative charge, you will recognize this. And by the way, the experiment that you guys normally will do in school is also in this picture. On the left, you have the magnetic field going from the north towards the south. And on the right, you have iron filaments. These iron filaments are placed all around the magnet, and we use them to analyze the geometry or the shape of the magnetic field around the poles of the magnet. That's very interesting, right? And this experiment can actually be recreated very nicely in the lab. We talked already about this, the magnetic field on the Earth. The north pole of a magnet is attracted to the south. The north pole of a compass needle points to the north, right? So even though the magnetic field goes from north to south, we have that the needle is always pointing towards the north due to the direction of the magnetic force. Something that I always tell students, maybe in your case, you don't have to worry so much about it. It would be more if you were doing calculations with magnetic fields and forces. But an interesting aspect about magnetic fields and forces is that all of them act in 3D. in electrostatics, right, we were easily able to study electricity, electric fields, electric potential, current, all on the plane. However, with magnetism, we cannot do that because there is something called the right-hand rule. And magnetic field can go horizontally, vertically, or out or into the page. I will try to show you that a little bit later, guys. Just remember that the magnetic field, okay, can be studied by observing the interactions of a moving charge inside a region of a magnetic field. And this allows us to have several applications. We can have applications in particle accelerators. If you have a magnetic field and you have charges moving within a magnetic field, these charges will be deflected, just like the needle in the compass, due to the magnetic force. And this magnetic force doesn't really act on the direction the charge is moving. Okay? Look at the difference between the magnetic field between the north and south poles of a magnet and the electric field between the positive and negative charge. Of course, if we were to put together the positive and negative charge, like not together but close to each other, you will see electric field lines leaving the positive here, there, going towards the negative. And the shape will be similar to this shape. However, even though there are similarities, the big difference is that in magnetism, the north and south always come together. In electrostatics, however, you were able to divide the positive and negative charge. Okay? So, nowadays, we always argue about quantum fluctuations and quantum theory. We have been able to study electromagnetism at the quantum level. And I did mention the strong and weak forces in nature, the nuclear forces. We have also been able to study them in the quantum, with quantum models, sorry. So we can quantize those forces and fields. The only force that we haven't been able to do to study at a quantum level is gravity. And you can probably guess why. The force of gravity depends on the mass and the gravitational field surrounding it, right? In this case, the gravity of the Earth. In the case of the mass of a proton, of an electron, right, are very tiny. So the force of gravity doesn't really exert much of or almost no force. Exerts almost no force. So it's very hard to come with a model to quantize gravity. However, modern theories indicate the existence of an elementary particle, right, that could lead us to the quantization of gravity. You probably have heard about it, especially in Marvel Comics. It's called graviton. All right. Now, if we put that aside, the electromagnetic force, nuclear force, strong and weak, are the only forces that we can actually study with this level of detail. And you know what's the interesting part? That the first force that we discovered was gravity. The first force that we studied in depth, right? Newton's laws, Galileo, then even Einstein, right? Among other physicists, right? is gravity. But we haven't really found much detail of the core of how it really works. We know the evidences of gravity, but not really the mechanism. Now, what I was talking about is that besides that, there are also quantum models for elementary particles with one single magnetic pole, magnetic monopoles. Again, we haven't really found anything like that. That's why I referred at the beginning of class as exotic materials. They might exist, but in exotic environments. Maybe in like neutron or white dwarfs, neutron stars. You know, maybe that's where we should go and find or try to locate those. Anyway, this is a nice concept map that allows you guys to look at the similarities and also the differences between electrostatics or electrostatic fields or electric fields and magnetic fields. Now, why do we call it magnetostatic electrostatics? Because if you remember, in electrostatic, we talk about charges that are there, point charges that are not moving. All right? In the case of magnetostatic fields, we are also discussing about fields due to a uniform magnetic field, so it's constant, but also we are talking about materials who are acting due to the existence of this magnetic field. We are not talking about current yet. That's going to come in a bit. If you were to have this question, an iron nail is brought near a magnet, which of the following is not true? Number one, the nail has both, the nail doesn't really have the poles. It becomes either north or south, depending on which direction you have the magnet at. Okay? And depending on the direction and the pole, you can have an attractive or repelling. Normally it's attractive because this nail normally is a ferromagnetic material, so that's why. Okay? So, by action-reaction, Newton's third law, if the magnet exerts an attractive force on the nail also exerts an attractive force on the magnet. So that still holds. Newton's third law. Even though we're going more into classical, we're leaving more the classical part of physics, going into the quantum part, right? But still, in magnetic fields and electric fields, we can still use that. Now, remember this, right? But we also have this. We have equipment in life, like electric motors, generators, electric guitars, microphones like that. We have different materials in life that we also use, like for example a hairdryer, automobiles. We have different materials, we have different technology that work using electricity and magnetism. This is where you can start thinking about how electricity gets together or gets joined with magnetism. The easy way to explain this is by saying that you induce currents using Faraday's law. However, I don't want to go there yet, okay? But let's go into the interaction between electricity and magnetism. Then we can talk about the induction process. You remember that when there is an electric field, right? So now I'm going to use a whiteboard because it will be better. Okay. Okay. So when we have a charge moving electric field. If the charge is positive, the charge will move on the same direction as the field. Now, of course, remember that we assume the test charge to be positive, right? So, if you have an electric field pointing like that, then if you have a positive charge, the charge will move in this direction due to an electric force. And we already know from last class that the electric field is the electric force per unit charge. What do we know about the interactions of charges and magnetic field? I want to do both. The charge and also I want to go into the current. They also go together. Remember that current is the transfer of electrons. Okay? Is the flow of charge per unit time. Right? That was current. If you have a charge Q and you have an electric field, look, the electric field actually the charge needs to be moving. If the charge is not moving, there is no sort of an interaction between the charge and the electric field. There is no deflection or anything. So the charge needs to be moving with some velocity. So it's a moving charge. Now I will draw an electric field. Sorry, magnetic field. So we have this, and obviously based on this electric fields, you will think that the charge will move like this. But no. Magnetic forces act on 3 dimensions. So even though this is not really going to be tested, I want you guys to learn that there is something called the right hand rule. The right hand rule allows you to use your right hand to determine in which direction the charge will move inside a magnetic field. What I do is I put my hand like this and I cure my fingers in the direction of the magnetic field. My thumb tells you how the charge will move. So it's moving towards you. So the charge will be doing this, even though the field is going up. Because that's how the magnetic force acts. Okay? Is there an equation? Yes, there are equations for this. We don't really need to go much into that. Okay? But that is important to know how the needle in a compass is deflected. Alright? But also to understand that a moving electric charge can also produce a magnetic field in the space around it. Alright? You can either have a magnetic field or it can be produced by the charge moving. So a charge cannot just be stationary like we do for the electric field. A charge has to move, which brings us to current. And by the way, guys, remember the molten core and the iron core? How do we have a magnetic field surrounding the Earth? Because the molten core is spinning. So you need to have conducting material, charges spinning. In fact, guys, if you have a current, we label it I, right? The current I, there will be a magnetic field around it. Okay. Direction-wise, it's a bit complicated to do it on the whiteboard, but there is a trick though. In physics, we say that this symbol means into the page. And this symbol means out of the page. Like the tip of an arrow and the tail. Alright? There. By the way, this can be used in particle accelerators and just in different conducting materials. Like for example, when you guys, and this is very important when we talk about electricity and magnetism. If you open a computer motherboard or a computer fan, most likely you will find more than one or at least one coil. Different coils can be used for different aspects in magnetism, but normally coil is used as a device or as a source of magnetic field. Okay? There are different types of coils. It can be the circular coil, it can be a solenoid, or it can be a toroid. Now, the one that we use more in physics is the solenoid. The solenoid is a pipe, it's a conducting pipe where you wrap around conducting cable, maybe copper. And what you can do as well is you can plug the ends to a battery. If you have a current moving, just as you are seeing there in the picture, you will have a magnetic field. The circles that you see there around the bar or around the charge are what we call Amperian loops, or just to keep it easy, magnetic loops. They give you the direction of the magnetic field in that region in particular. The magnetic field actually depends on either the strength of the current and the distance from the point, or the distance from the source. That's why, okay, let's keep talking about the planets and astronomy. Jupiter and Saturn, they have very strong magnetic fields. Now, they don't have an iron, nickel, molten core. They actually have a rocky core. No surface, but a core mostly made of rocky material. What we know about those planets is that they are made of gas. They are the gas giants. But they also have, especially Jupiter, the strongest and more intense magnetic fields in the solar system. Now, there are different mechanisms, as you are seeing right now, to produce a magnetic field. It can be either by a current, by a moving charge, right? But it can also be due to the motion of conducting material, like here on Earth. So, what conductive material is there in Jupiter to create or to form such a strong magnetic field? Liquid metallic hydrogen. That particular state of matter of hydrogen, which is very exotic, very weird, and we can only find it in the gas giants, also in Saturn, is spinning all over the mantle though, or what we will call the mantle here on Earth. That produces a very strong magnetic field. Evidences for that: auroras in the poles of Jupiter. We have seen auroras. If you Google that, you can probably see a few pictures of those. Okay, so I don't think I need to go over this a lot. You can see how when there is no current on the left, no deflection of the compass. As soon as you put a current through the wire, then you have a deflection on the compass, magnetic field. Okay. Remember this? Batteries and DC current. In the previous chapter, we discussed about DC and AC current. DC is direct current, constant. It never changes. AC current, however, is what we call an alternate current. And it has that sinusoidal shape, remember that I showed you in the last slide, in the last lecture? So the current is not constant. You can get an RMS value, that's fine, but still, it's not. So to study DC currents, because AC currents, believe it or not, they are easier to produce or to find in households, in AC generators, all right? You will have AC current being produced. In fact, for a science fair experiment, I remember helping a kid developing a device that will convert from AC to DC using a nice diode. A diode in physics, we use it in circuits to keep the same direction of current, or sometimes to switch it a little bit. So that's important. And we were actually very successful. We were able to convert, we converted AC current to DC current. So that was actually very neat. Can you go the other way around? That's more complicated. I know you can do DC to AC using a diode and using coil, like a solenoid. That's actually the principle of the Faraday flashlight. So let's go into that. We've been discussing about electricity and magnetism. Let's show you a little bit of what I mean by the Faraday flashlight and the Faraday experiment. So, an electromagnet. You have a coil with a length that is larger than the diameter itself of the solenoid. By the way, there is a solenoid there. You see here? Okay, imagine the white is a pipe. You have cable wrapped around. Each turn increases the intensity of the magnetic field. The more turns, the more field. Okay. The magnetic pole associated with the coil's field nearest to the rod induces a magnetic field with the opposite. Okay. So what this is telling you is this. When you connect a battery to a coil that you see there, and you introduce a magnet into it, you will have an induced current and magnetic field. If you have a current, you have a magnetic field. Alright. How is that possible? Well, when I describe you the idea of a solenoid, you have to think about, and I'm going to use a picture from the internet now because it's easier. I could draw it on the board, but it will take too much time. Just to show you what a solenoid is in real life. It's a very important source of magnetic field, by the way. Oh, there it is. So this is a typical solenoid we use in the lab. There. You can see there can be hundreds of turns in here. So, if we connect the solenoid to a battery, in this pin, right? You have a current going here, but it's going in circles, right? So it's possible for us to find the poles of the solenoid by knowing the direction of the current, by using the right-hand rule. What I want you guys to just learn from this is that if there's a current flowing in a solenoid, automatically you get poles like a magnet. Hence, an electromagnet. Now, what is the idea behind introducing a magnet inside a solenoid? For example, you see the solenoid here? You see those holes in there? We can try to introduce a magnet in there. And that is a Faraday experiment, guys. The Faraday experiment what's the idea of the induction of electricity? There. So, if you have a magnet and you have now the coil, the solenoid, is going to be plugged to a galvanometer. Okay, in the lab or in general, you probably are used to ammeter and multimeters. We use them to measure current. There was one here. Oh, there it is. Let me bring one. Okay, so a multimeter is a device that we use here in the lab to measure current. And I like using this because these are digital ones and they give you very accurate readings. But you see this, right? We can use this device to measure current or voltage. Is it on? Oh, it's dead. But if we connect this to a solenoid and then we move a magnet towards what we call the coil, this guy will start reading, depending also how strong and how fast. What do I mean by how fast? You have the magnet going in and out of the solenoid. We do that to induce a voltage in the coil. And if there is a voltage and the coil has some sort of resistance, minimum, but there is some resistance, what do we have? Current. You remember from Ohm's law, V over R equals to I, current. So this device can be used to measure also alternate currents. Because guess what? That current that you guys are producing is not really direct, it's alternate current. And this device can measure that. So, what is the idea behind an electromagnet? Is producing electricity using a magnet. That's basically what it is. Faraday experiment uses two coils, a primary and a secondary. Instead of using a magnet, you can have a primary coil, which is your solenoid, and a secondary coil, which we purposely connect to a power supply. So the secondary coil has current flowing. If you place it inside and outside of the primary coil, you get an induced current. Without touching, by the way. They don't need to touch. Without some sort of interaction. Well, besides the motion itself, right? That is very important, guys. Because when you introduce a magnet or a secondary coil inside a primary coil, guys, you are changing the flux of magnetic field. What is the flux of magnetic field? It's the idea of magnetic field lines going through a surface. If you have a surface, you can have magnetic field lines not like that. You can have magnetic field lines going like this. They are crossing, they are going through this. So there is some sort of flux. The more lines, the more flux. By changing that flux, we get an induced voltage and electricity. Okay? As I mentioned before, right, there are several equations that one of the few ones that we are going to be talking about is the one that relates to transformers. Because right now we are studying how electricity is produced by a changing magnetic field, a changing flux, right? Which is basically the electromagnet. There. As the magnet goes towards the loop or the coil, the flux is changing. If you move it away, the flux decreases. If you move it towards this, the flux increases. So this needle here will start being deflected, and it will read some current. Oh, by the way, what's a galvanometer? A galvanometer is like this, but analog. And a galvanometer uses magnetic forces to read the current. All right? Okay. What is this? Well, you know what you're seeing right now there, guys? You are seeing the insides of a particle accelerator. There are two particle accelerators that you guys should know. The Fermi Lab in Chicago and the LHC, Large Hadron Collider in Switzerland. 10 years ago, approximately 10 years ago, when they turned on the LHC, when they turned on the LHC, they thought that it was going to be like this year, 2020, like the end of the world. Because this device, the objective of this device was to recreate the initial conditions of the universe. In other words, recreate the Big Bang, the big explosion. We know now, after 10 years, that nothing happened, right? What we have is that we have hadrons, which are positive charges, protons, colliding at extremely high speeds. And the way we calibrate the velocity and the trajectory of this is by calibrating the magnetic field. Now you know that the magnetic field can deflect. And we use that for what we know as the synchrotron radiation and synchrotron radiation. Right. Anyway, that's going a little bit beyond, but just so you guys know, we have applications for that in real life. We've talked about that already. And I did say this before, right? A magnetic field exerts a force on a moving charge. So remember, how do we study, or how do we know about the existence of an electric field? By the interaction of the charges in certain region, if they move away or towards a certain point. In here is similar. We know about the existence of a magnetic field by looking at the deflection of a particle, or a charge in this case, in a region where there is a magnetic field. And that's where you have the magnetic force. So this relates to this that we talked before, and also this in between the magnets. All right. Even though it's not say, they don't show it there. What you guys are seeing right now in there is the right-hand rule. If you put your 4 fingers, and you can try to do it right now at home, put your 4 fingers in the direction of the current, and then curl your fingers in the direction of this field. Right? So you may want to put your hand in such a way that you can curl your fingers in the direction of those arrows here, these ones, these 3 arrows. You will see that your thumb will go upwards. Well, that's why the force is going up. But look what happens if I change the direction of the current. Now the force goes downwards. How can we use, just by changing the direction of the current, we can reverse the polarity, in other words. How can we use this in real life? We can use this in real life by placing a coil, like that. So you can have this coil that is rotating. And why do we care about rotation? Because that's the idea behind a generator. All right? A generator or even an electric motor. All right? In this case, you have a coil of wire that is mounted so that it can rotate inside a magnetic field. So if you have a current that is constant, so a DC current flowing through the coil, at some point it's going to go in one direction, at some point it's going to go in another direction. So that's why we have this coil rotating, because of the change of direction. Okay. Okay. This is actually very interesting. So now that we talk about magnets moving through coils and producing currents, right? Inducing. The right term is induce. Okay? After the class, I'm gonna give you guys a couple of videos I want you guys to watch. They are not very long. And they are mostly about a lot of the theory behind induction. Don't worry so much about the mathematics, because there's plenty of math. In fact, that's how we measure how much energy can be released by a magnetic field, right? Just like we have electric energy, we can have magnetic energy. And we can have what we call inductors. But that's not the scope of this course. It's more to understand the physics behind these processes. So, just as you can have a magnet that is moving inside a coil, inducing a current, because you have this current and you have this field, the fact that the magnet is producing that current also implies that it will produce an electric field. I mean, I can prove that with equations, but let me just put it in this way. When you have a magnet going inside a coil, in and out, you have an induced voltage. Therefore, you have a current. The current doesn't appear from nowhere. The current appears because there is a voltage. And then V over R, current. Where does the electric field come from? I don't think I mentioned this. Actually, I did. When we talk about capacitors. In capacitors, which are devices that we use in electricity to store electrical energy, we have that the electric field is proportional to the voltage produced or input. So you have a voltage in a capacitor. The electric field is proportional to it. So if we have a voltage induced in a coil, we have an electric field. And guess what? That's basically how we finalize the joint between an electric field and a magnetic field. It's harder to measure electric fields. So what we measure are voltages that you're seeing there. All right, or current. Normally, the electric field around the magnet is going to be in the shape of circles. Okay? So, this circular field will force charges in a coil to move in the same direction as current. Hence, you have the induced current that is just moving in an opposite direction. And by the way, I didn't really emphasize why charges move or why the current induced will be in an opposite direction. There is this whole idea of Lenz's law. But just think it this way. if you have a coil or you have a region, a current moving, and you have a magnetic field, if this current induces a magnetic field, a magnetic pole, and a current in a secondary circuit, this secondary circuit will have a direction of current opposite to whatever produced the current in the first place. So if there's a counterclockwise current in a circuit and you have another circuit right next to it, that other circuit will have a current clockwise. So it will induce a current in the opposite direction. All right? That is very important when we talk about induction and generators. Okay? Guys, all your iPads, tablets, computers, a lot of our devices, they use these principles. Induction, current, DC, AC. So there are a lot of applications. A generator, actually. Right? Remember when I talked to you guys about that AC current? And that's why I like to introduce AC current more in this section. Because AC current, and we can actually review that concept right now. AC current is normally produced by mechanical energy being transformed into electrical energy. For example, a waterfall. Now, it doesn't magically get transformed or transferred. You need to have a generator at the bottom, which are basically coils. And then you have a generator and you have coils spinning really fast. The faster they move, the stronger the voltage induced will be. This voltage will actually be used to actually illuminate a city. All right? So, when electric charges or magnets are moving, electricity and magnetism they depend on each other. They are not independent anymore. So, motion, guys. If there is no motion, you can treat them separately. But everything is moving anyway, right? Charges, current, coils, the water from a waterfall, everything is moving. So there is always going to be a connection between electricity and magnetism. All right? It's another concept map here. All right? With a magnet, charged particles, magnetic field, electric field. Okay? Remember, changing electric field induces a magnetic field and vice versa. Nothing is constant, like you know from physics. Well, we already did that at the beginning, but there is no point to talk about motion without acceleration. Most of the time there's either slowing down or acceleration, right? So the electric field and magnetic field in every region that we know is always changing. So one is always inducing the other one. All right? All right, let's see these questions here. A stationary electric charge produces a magnetic field. True or false? What do you think? If it's stationary. If it's stationary, it doesn't produce any field, so it's false. It's a current, a moving charge, the one that produces a magnetic field. How does one reverse the polarity of an electromagnet? Remember the Faraday experiment. How will you reverse the polarity of an electromagnet? Electro comes from electricity, current. So what do you have to do with the current? You have to change its direction, okay? you will reverse the current. You will change the direction of the current. All right? And related to the first question, a magnetic field exerts a force on an electric charge if the charge is what? What needs to be happening with the charge? So there is a force acting on it. The charge must be moving. Okay? Okay, we can do it. Okay, this one is good one. When the coil in a simple electric motor is turned by a crank, for example, right? The motor functions as what? The electric motors are normally used as generators, guys. Those generate, I mean, now you can actually understand, for example, yeah, even in daily life, right? If there is a very cold day of winter and your heat stops working, the electricity stops working, right? Gas. You can use a generator. And normally what do? You turn it on by moving what? A coil inside a generator. That's what's rotating. As you move it faster and faster, stronger and stronger, right? Then you will see the current being produced, being induced in there. All right? Or the same with a jet. When you want to turn on the engine of a jet, sometimes you are doing the motion, right? You've seen it in movies probably. So that's basically the idea there. Okay? So what do we have left? Because now we can talk next class about transformers. All right. We will do some equations and then applications of this, for example, in mobile phones or metal detectors. And some applications of Faraday's law, for example, speakers, microphones, there, all right, where you have an electromagnet. And then we can go into electromagnetic waves. Electromagnetic waves will be the last topic we will discuss next class. And then that will be the topics for your exam: electricity, electromagnetism, and electromagnetic waves. Very conceptual. However, before we finish, I want you guys to take a look at the sample problems for electricity. If you guys go to the Canvas, besides the web assign, there are sample problems here for week 8. And trust me, they are very simple. They give you the current, they give you the time, they ask you for the amount of electrons. Remember, charge divided by time is current. If you find the charge is a multiple of the charge of the electron. So that's how you answer this question. You have the equation of power with voltage and current. So it's actually pretty simple. I might actually try and do a couple of these problems next class as to help you for the exam on Tuesday. But you guys, I think you guys should be fine. Okay, guys. So that's it. I'm going to stop class right now. And if you have any questions, please feel free to drop them in Canvas. Okay? And I will see you guys next class on Thursday.